Good morning, my YouTube viewers. It is Crystal here. I'm just here this morning because I wanted to do another code review. On my last video, I did a code review on a neural network made in NumPy to make predictions on the iris dataset. And what I'm going to do on this particular code review is I translated the code from NumPy to JAX. And whenever I translated the code to JAX, I had to do a few little things because although JAX is written very similar to NumPy, there are some things that you can't do in JAX that you can do in NumPy. And the reason for that is because the arrays in JAX are immutable. And so you can't change the information in an array in JAX, so you have to work around that. And there's some other things as well. I was thinking about something, and then I just it slipped my mind as I was talking to you about the arrays in JAX. But what we'll do is we'll go through the code review. Oh, and it's also the random number generator in JAX is different from the random number generator in NumPy, and as a result of that, you have to use different coding mechanisms to accomplish the same task. So those are some differences between JAX and NumPy, and that's why I wanted to give you this code review. So the first thing that we're going to do is we're going to import JAX, and that's going to create your neural network. And then we're going to import sklearn, and what sklearn is going to do is going to give you your machine learning functionality and also give you your data sets. And then after we've imported the libraries that we want, we're going to load the iris data set. So X is your data and Y is your target. Oh, and before I forget, I also wanted to say that I put this code in Google Colab, which is a free online Jupyter notebook hosted by Google. It's a great platform to use except for the fact that it doesn't have an adequate undo function, so you have to be really careful not to delete or overwrite code. If you do delete or overwrite code, then you have to go back into the search engine and saved history, and you may get the code back from the saved history, but it's not always a guarantee. So now that I've told you what I made the program in and a little bit of information about Google Colab, we will continue with the code review. And what we're going to do is we've loaded our data set, we've loaded the iris data set, and we've got our X and our Y variables. And then what we're going to do is we're going to use sklearn standard scaler to scale the data. So the data is now scaled. Now we're going to one-hot encode the data. Now this is the difference between JAX and NumPy, because NumPy you use a different type of code, but the thing about JAX is because the arrays are immutable, you're not able to do filtering in JAX, and because you're not able to do filtering in JAX, you have to use different codes. So we're going to define in values as j and p dot max y plus 1, and the reason why is because in Python 0 is your first number, so you've got 3 outputs, and then it says y1 hot equals jnpi in values of y. So let's come over here. Well, we'll look at NumPy, and NumPy is close. It says NumPy Jack's NumPy I returns a 2D array with 1s on the diagonal and 0 elsewhere. So that's what your I is. So it returns 1s on the diagonal and 0 elsewhere. So that's how the I works. And then you got your Y1 hot. So we've got 0, 1, and 2. And now what we're going to do is we're going to split the data set between using sklearn's train test split. And then you'll notice that on the X variable, we've got 4 columns of data for the sepal and the petal and the iris data set. And then on the Y variable, we have 3 columns of data for the one encoded. Now what we're going to do is we're going to define our neural network. So we're going to define the sigmoid function. So the sigmoid function are simply mathematical equations that equate all values of x to an output ranging between 0 and 1, thus creating an x-shaped graph. So there's your sigmoid function. And we're going to also define the sigmoid derivative. I hope I've spelled that correctly. The derivative of the sigmoid function is the sigmoid function multiplied sigmoid x multiplied 1 minus sigmoid x. And so it says a sigmoid function is a bounded differentiable real function that is defined by all real input values as a non-negative derivative at each point and exactly 1 inflection point. So we'll just leave it there. And then we're going to define the neural network architecture. So input neurons is the shape of X train. Hidden neurons is going to be 8. So what they've done is they've just multiplied the columns of the iris dataset by 2. And output neurons is going to be num classes. And you've got 3 classes. We're going to initialize the weights and the biases. So you set your random number. So the random number is done differently in JAX. Key equals jax.random.prng key 42. And then the random uniform is done differently in JAX than it is in NumPy. Because NumPy, they look for the size, and in JAX, they look for the shape. So weights input hidden equals jax.random.uniform key, comma, shape equals input neurons, hidden neurons. Bias is hidden equals JNP0, 1, comma, hidden neurons. So let's look up zeros, JNP zeros. Returns a new array of a given shape and type filled with zeros. So it gives you an array filled with zeros. So the shape is going to be 1, comma, hidden neurons. So That's what it says, 1 comma hidden neurons. And shape is an inch or a tuple. And one of the bad things about JAX is it doesn't give you code examples, whereas in NumPy it gives you code examples. So I guess they just don't give you very many code examples because they are expecting that you would know NumPy before you would know JAX. But JAX is a little bit different from NumPy, even though it's similar. So now we've got weights hidden output equals jax.random.uniform. Key shape equals hidden neurons, output neurons. Bias output equals JNP zeros, 1, and output neurons. And now we set up our hyperparameters. Learning rate is 0.01 and epochs is 10,000. So now we set up our training network. So this is where we're going to train the data, the training data. So we're going to set up our forward propagation. So if we come over here, forward propagation in neural networks is where input data is fed through a network in a forward direction to generate an output. The data is accepted by hidden layers and processed as per the activation function and moves to the successive layer. So that's what your forward propagation is. And then, so hidden inputs equals JNP dot, that's dot product, X train weights input hidden plus bias is hidden. Hidden outputs equals sigmoid hidden outputs. Final outputs equals JNP dot dot. Hidden outputs weights hidden output plus bias output. Final outputs equals sigmoid final inputs. And then we calculate the error. Error equals Y train minus final outputs. So that's going to be your error. Now we're going to go into the back propagation. We say backpropagation is the essence of neural net training. It is the practice of fine-tuning the weights of a neural network based on the error rate obtained in the previous epoch. And proper tuning of the weights ensures lower error rates, making the model reliable by increasing its generalization. So that's your backpropagation. And then we're going to update the weights and biases. So weights hidden output equals weights hidden output plus hidden outputs dot t, that's transform, dot output error term times learning rate. Bias output equals bias outputs plus JNP dot sum error, output error term axis equals 0, keep dims equals true, times learning rate. Weights input hidden equals weights input hidden plus x train dot t dot hidden error term times learning rate. Hidden biases equals hidden biases plus JNP dot sum, hidden error term axis equals 0, keep dims equals true, learning rate. So that's how it trains the data, and it does it in a for loop. It says for epoch and range epochs. And so in some of the documentation, you'll see it equates it to an iteration. It's not an iteration. And what happens is, it says epoch and range epochs. it will iterate through each example in the data set. So 10,000 times the number of epochs. So it will iterate through each example in the data set. So we've got 100. We have 150 values in the iris data set, but we're not using all of those 150 values. So I'm just going to say 110. Okay. So it will iterate through each example in the data set, which is 110, and then it will iterate through that through each epochs. So let's say you've got 10 epochs, which we don't have 10 epochs, we've got 10,000 epochs. But let's say we've got 10 epochs and you've got 110 examples. So what it's going to do, it's going to iterate it 110 times 10, which is going to be 1,100. But since we're doing 10,000 epochs, I think it's going to be more like 100,000, 110,000. We'll say that. I haven't got a calculator with me, so I could be wrong. But I'm just trying to explain to you the difference between an epoch and an iteration. And then when you see it on the internet, sometimes people equate epoch to an iteration, but an epoch is not an iteration. An epoch is the number of iterations times the number of examples. So there is a difference between an epoch and an iteration. Sometimes when you're looking on data on the internet, they'll call it an iteration, but it's not an iteration, it's an epoch. Now we're going to test the neural network. So hidden layer input equals JNP dot dot, that's your dot product, X test, weights input hidden plus bias is hidden. Hidden layer output equals sigmoid hidden layer input. Output equals JNP dot dot, hidden layer output, comma, weights hidden output plus bias output. Predicted output equals sigmoid output. And we're going to print the predicted output. So you'll see that your output is going to be in a matrix that has 3 columns of data, and it's going to be in a float. So now we're going to convert the one-hot encoded predictions to class labels. Predicted labels equals JNP.max. Predicted output axis equals 1. Print predicted labels, and then you're going to print your JNP.argmax y-test axis equals 1. So what you do here is you're just going to, since this is a small data set, you're just going to compare the predictions to the label, to the true labels. And fortunately, in this particular example, we had 100% accuracy because we calculate the accuracy. Accuracy equals JNP.mean. Predicted labels equals y-test.argmax axis equals 1. And then we print our accuracy. And in this one, we've got 100%, which is great. And you're not always going to get 100%, which is why we decided to use the iris data set, because it's a real easy data set to use. So I've been talking for almost 20 minutes in this code review, so I'm going to go ahead and conclude this video. So I would like to thank all of my subscribers for supporting me. If you like this channel, this video, please like, subscribe, and share. If you want to be notified whenever I make a new video, please tap onto the bell button next to the subscribe button. And please thank you very much for watching my video. I look forward to making more videos for you in the future.